multinazionale, il CNE.
Morning, so this morning Marcel is going to tell us about Hamiltonian models, which I hope is quite wide interest, so off you go.
Okay, thank you. So let me start by thanking the organizers of this workshop and the Newton Institute also for what has been so far a very productive and enjoyable stay. So today I want to basically give a elementary overview of some of the things we've been thinking about over the last few years. So there won't be much new today. So next week on the workshop I'll be reporting on some more recent numerical results on the models that we have been studying. And I think Sergei Vasilkevich, who is one of my collaborators on this, will talk about varying Coriolis parameter issues in these models. So let me also say that a lot of what I'm talking about has been developed in collaboration with Sergei. There's also input from Georg Gottwald, who is at Sydney, and my former PhD student Mahmoud Charlik. And more recently we have been starting doing numerical simulations on these models with David Ritchell at St. Andrews. Right, so just to fix the framework that I will be speaking about today, so we are talking about as just a simple model problem, the rotating shallow water equations, mainly on the F-plane today. So to fix notation, I'll write them in this way, plus u perp for the Coriolis term, and then plus a Berger number over epsilon height gradient equals to 0. And then we have the continuity equation plus the divergence of HU equals 0. And there are essentially two important distinguished limits. So there is the QG limit, where we heard a lot about, because one can sort of do beautiful analytical work on essentially the fast rotation limit, and that is distinguished by having the Berger number, so the BU of order 1, and then in order to get a leading order geostrophic balance between pressure gradient and Coriolis force, one has to assume in the QG limit that height variations are small. Right, so this is not what I'll be concerned with today, at least. So we are going to be in the SG limit, where the Berger number is of order Rossby number epsilon, and this shall be the only small parameter in anything that's going to follow. Right, so I shall be working mainly in the Lagrangian framework of the Hamilton variational principle. So the main object of interest there is the flow map, that if I have my initial fluid container omega naught, let's say, and I label some point or fluid particle, if you want, by A, then the flow map maps this into the same or different fluid container at a later time. Just for visualization, I choose it to be different. Later I will of course work on a fixed domain. So Lagrangian label A is mapped onto Eulerian position X, and then I have a local speed here, so an Eulerian variable c of x comma t, and that's of course if I translate into Lagrangian variables. Okay, so the map is called eta in my notation here, so it will be eta dot at A and T. So that's the notation I'll be using here. And then it turns out that the shallow water equations, as written here, can be derived as the Euler-Lagrange equations of a variational principle by setting to 0 the variation of the action which is the time integral of the Lagrangian, and the Lagrangian in this case is given by a function r. So this is a function of Eulerian variables, and I shall always indicate explicitly any transition between Lagrangian and Eulerian variables. So I'm going to integrate over Lagrangian labels here. So I compose with eta dotted with velocity, so eta dot here, and then to get the scaling right, I have an epsilon over 2 here, eta dot squared, and then minus 1/2 kinetic energy term. And this integral is over labels if I write it in this way. Okay, so then I think I'm talking mainly to experts here, but let me still, just to set up the framework here, explain one of the prominent features of this construction here. So via the Noether theorem, one has a direct correspondence between symmetries in this Lagrangian or any other Lagrangian and the conservation laws of the equation. And the interesting symmetries here are time translation symmetry, that's very classical, gives rise to the conservation of energy in any Hamiltonian system. So I'm not going to talk about that explicitly here. But the more interesting, or at least more subtle feature of fluid dynamical equations is the particle relabeling symmetry. And let me take a few moments to show you how particle relabeling actually leads to potential vorticity as we know it. It's in principle well-known derivation. It's can be found in many books. For example, it's in Salmon's book on geophysical fluid dynamics. Some of these derivations are hard to follow, so let me just present sort of what I think is a quick version of seeing what is happening there.
This derivational principle is like a Lagrange form where the principal variable is eta, the arguments are eta and eta prime, so the eta dt. So what is h in terms of eta?
Right. So this is something.
I know, but I'm not sure if everyone here.
No, thank you, because
I to close the problem. That's basically what I'm doing.
Yes. Thank you very much for asking me
And the same
to do that.
for R, I guess. Especially H.
Yes. So for the R, I think we'll come to that. But your honest remark is, I guess, really on time here. So basically, all the information of the flow is encoded in the flow map, especially also the mass transport. So by the Liouville theorem, the continuity equation in Eulerian variables is related to the Jacobian of the flow, and I can write that in the following way. So H composed eta is, and let me, without loss of generality, sort of assume at least at some virtual initial time, I have a flat surface or uniform mass distribution, which is not a restriction in any way. So it's the inverse Jacobian of the flow. Right, and
it's with the gradient is here with respect to A, right?
with respect to A, because I'm always differentiating with respect to the natural arguments.
I know, but I'm
Yeah,
just
no.
trying to play it.
Yeah, thank you. Right, and I'm setting up, well, in general, this function R. We'll see how that arises, that the curl of R is the Coriolis parameter f, which for purposes of this talk I will assume to be 1.
Now this gradient is with respect to the arguments, and that's with
Right,
A
so
prime, right?
the natural arguments of R are Eulerian positions. So
That's often very confusing for people.
Right, so I think that is sort of a question of community, so coming from sort of more, let's say, PD analysis, I find it confusing to have implicit arguments, and I can imagine it's the other way around for people being used to those. Right. So what is the particle relabeling symmetry? Well, it's the notion that the physics of the problem, and in particular the equations of motion that I'm getting out of there, shouldn't depend on the particular choice of label. So in other words, if I mix up my initial labels, I should get the same equations of motion. And in this expression that's on the technical level encoded by the fact that I can compose the Lagrangian by a volume-preserving map, and nothing will change in this integral. Right, so what I'm going to take here to do particle relabeling variations is I'm going to parameterize a curve in the group of diffeomorphisms in the following way. So I'm taking my flow map to this problem, and I'm composing that with a volume-preserving map or curve of in the volume-preserving maps. And then
Sorry, just continue to interrupt the line. Oh no, so what do you mean by volume-preserving map in this context?
map with Jacobian ones.
So what's the definition? Is it mass conserving or area conserving?
It's area conserving here, because we need to exploit the symmetry here in the Lagrangian. It is really just, I'm integrating over area, so that is what I should be preserving here.
For some purposes you might want the opposite choice, that's all.
Right.
Yeah, so different choice, it always
yeah,
what I'm doing, doesn't it?
Yeah, so what I'm trying to get at is just here PV conservation, and then if I define the variation of eta as d eta epsilon by d epsilon at epsilon equals to 0, then well, what I would like is that at epsilon equals to 0 my family of maps here is the identity, so then what I get here is gradient of eta and then the variation of phi, and since I've assumed this to be volume preserving, this is a vector field and it's divergence free. So this will come up.
Now I'm just want to keep interrupting. So in this, if you're doing to the order, obviously it's the natural thing to do, but in this problem it's not so obvious it's the natural thing to do. So why is it the natural thing to do?
Because I'm not, this is not supposed to be, this map here is not supposed to be real flow. It's essentially encoding the symmetry that I find in the Lagrangian. And that basically, if I were to transport mass, I would be actually changing my physics, because transporting mass from here to there is going to give you a different Eulerian mass field, and therefore it's not a symmetry of the Lagrangian.
Yeah, well, that might be in terms of relating this to that, and it might be an interesting issue. Well, I'll shut up at this point.
Right. So, yeah. So. You'll see the PV pop out, and I hope then.
Yeah, but I'll defer further discussion of that till afterwards.
Right. So now, to derive the equations of motion, what we need to do, this is classical mechanics in some sense, take variations, arbitrary variations of the flow map without any divergence constraint on the vector field, and hold these variations constant at the temporal endpoints, and that means we can freely integrate by parts in time. We assume that we can integrate by parts in space as well. But with these type of variations, so these are not time dependent, so I cannot assume that they vanish at the temporal endpoints. And so what I get here, if I take variations of the action, I get, so this is just chain rule plus epsilon plus further terms that I'm not concerned with here. And well, the game in all of these Hamilton principal derivations is to now use integration by parts to move the time derivatives of the variation. And so there are essentially two terms where I need to integrate by parts. And so if I do that, I essentially generate the full integral terms that lead to my equations of motion, plus I get now temporal boundary terms. And so let me just indicate what boundary terms I'm getting. So from integration by parts, so let me denote it by an equal sign in quotes. So I will get minus r dotted with a variation of eta, and here the same plus epsilon eta dotted with a variation of eta at t2, t1. So that was the time integral here from t1 to t2, plus terms that once we assume that we are on a trajectory of the system, will all duly cancel out with the remaining terms. So that's a computation that I don't want to show here. So the music for the Noether theorem really comes from these boundary terms, and there is a space integral still. So dA. And now it helps, if I look at these terms, to be a little bit more abstract. Well, let me first insert the variations. Sorry, this is plus here. So r plus epsilon eta dot composed eta, and then from this little computation here I have this here dA, and in the temporal limits. Right, and now this one, if we interpret this one as a one form acting on a vector field, so it's basically this duality inner product, we can recognize this one here as the pullback of a one form, which I might write abstractly as well, or half abstractly as. And this one here that is paired with it, well, it's divergence free, so it's d of something. So let's write d of psi. And we're integrating over labels. And now I integrate by parts, assuming I have my boundary conditions fixed up in the proper way. So I move the d on this term, and now I use the fact that pullback and exterior derivative commute. So what I get is that this is minus the pullback of d r plus eta epsilon dot acting on psi. Right, now technically speaking, this is now a two form, which if I identify it in the usual way with the scalar field, but this is the pullback of a two form, so from there I get a wedge product that through the identification with the scalar field actually collapses to the determinant, and therefore, since the function psi, so this variation vector field here is arbitrary, well, first of all, I find that the pullback of dr plus epsilon eta dot at time t equals t2 is the same thing at time t1. So that's basically conservation, and now I have to work out what it is. And by the fact that this needs to be interpreted as a two-form, what I really find is that the quantity now back in sort of coordinate vector notation, the curl of r plus epsilon u, yeah, this is composed eta here, no, this should be u, plus epsilon u divided by h. So that's the Jacobian factor that comes in through this identification of two forms with scalar fields, that this is the conserved quantity, and we have recovered the well-known PV conservation law for shallow water. Right, so one can do this computation also in coordinates. It's a bit of a mess, but one can surely work through that. And the main point is that the particle relabeling symmetry, being just the change of variables formula for this integral, is a very robust object. So whatever you do on the Lagrangian, you cannot really destroy that symmetry. So whatever models you develop by changing terms in the Lagrangian, you will always get conserved potential vorticity, so material conserved potential vorticity. And that has been basically described and explored by Salmon a lot starting in the 1980s. And that's the philosophy that I'll be taking also in the following. Yes?
So someone spotted this symmetry. How do you know that there are not more symmetries? Why is this? This is almost philosophical question. We seem to know the symmetries in the shallow water system, but how do you know that there are not more? How do you know that this specific variation is the one to take? Not a more general one.
No, I do not know.
Is there a way, do you know then, to figure out whether unforeseen symmetry?
I don't think not to my knowledge.
But you just have to spot it somehow.
One has to spot it, and there are probably physical reasons. Yeah.
I mean, somehow to have, if you, I mean, this classical mechanics. I mean, if you have enough integrable, if you have enough conserved quantity, you have an integrable system.
Yeah, but that's
So somehow it's an equivalent, more or less equivalent kind of question. So it should be unanswerable.
But this
essentially
unanswerable.
Yes, I mean, can you identify a system as integrable
Right.
easily? No,
Sure.
I mean,
no. Okay. And then I do have another question. I noticed that in Loede's article, she does not integrate by parts, and she gets the conservation law. So and some people do. Some does integrate by parts. So I think there is a way. There might be a way to do this without integration by parts.
Does she do shallow water? Did she do
No. But the point is the general machinery she sets up, right, using Loede's theorem. She doesn't use integration by parts, which I only saw recently,
Yeah.
and I was surprised by it.
Yeah, I have to admit I didn't read the original Noether work, but I can only speculate that this is something that is algebraically equivalent to integration by parts, and you just cast it in a different way. And if you basically track down what is done, that you'll see the correspondence between sort of this way of thinking about it and what she had proposed.
But the subtle and less subtle differences, then you don't need take into account boundary conditions, which you didn't need to, because you basically to periodic boundary conditions, right? It's worried about. But in case you have solid walls, actually the derivation without integration by parts is considerably easier in principle.
Right, so let's talk about that offline, I guess.
I certainly want to talk to you offline about whether this conservation principle has been created by using what I would have thought was an unnatural class of variations. But obviously it mathematically works, you can choose anything you like. I'm a little bit, well, I'll talk to you about this offline as well, because I'm slightly worried about it.
Well, at least the result is something
there's
you...
nothing mathematically wrong with it.
Yeah.
It's but in sort of doing variational arguments, essentially you choose any class of variations you like, and then everything goes through rigorously. I'm a bit uncomfortable about your divergence-free variations in this problem.
This is particle relabeling. This is not getting the Euler-Lagrange equation.
Okay, well,
So
let's talk about
when-
it offline.
when I'm-
Again, let's talk about it offline. I'll say
Right.
why.
So I didn't show you how I get the Euler-Lagrange equations, but it's basically full variations, and of course there's no divergence
I'd
condition.
like to show you really outside offline. I'd like to just show you why I'm uncomfortable about this.
Right, so now let's get to what I really want to do in the variational principle. So the basic idea is, since we have a small parameter here, the epsilon, which I saw kind of carried through, but didn't use explicitly yet, I would like to think of my flow map as essentially a family of flow maps that is parameterized by epsilon. And then I can essentially treat, so this is actually bad notation, I have to admit, because this epsilon from the parameterization of the variation obviously is not the Rossby number, but this is exactly what I'm going to do now. Namely, identify the physical small parameter with a parameterization of curves in the diffeomorphism group. So in particular, so now all my flow maps shall carry just for notational convenience this explicit parameter epsilon, and I can write a prime as denoting a derivative in epsilon, and so I can associate with it and take this as a definition a vector field V epsilon which generates a flow in the direction of the small parameter. So right now this is just formal nonsense at this point because I haven't done anything with it, but this is really the basic framework in which I want to move here. And just to be clear about it, so really in the end this flow map will be a 3-parameter family of maps. Namely, there's physical time, that's clear, that has always been there. Then there's epsilon, which we identify with the perturbation parameter here. And when I'm taking variations, I will of course also talk about a curve with a separate parameter in order to define what I mean by the variational derivative. Right.
V epsilon is what kind of object is V epsilon?
V epsilon is a vector field. Right.
On
It's a derivative
omega. On omega.
on omega, yes. So yeah, I'm assuming fixed domain. Right, so there are now essentially various ways of how to proceed. So I can insert essentially, or I can interpret my variational principle up there in the sense of admitting this additional parameter which is literally identified with epsilon, and then I can formally expand. So at this point everything I'm doing is formal, and I'll come to some analytical issues at the very end. So that means I can now, let me also use an epsilon subscript to denote that this is the full epsilon dependent problem, and then I can expand in a formal Taylor series which by various computations will read, well, quite obviously at the leading order, well, this is the first order term here, the kinetic energy, so at the leading order I'll replicate these two leading order terms, so no surprise there. Minus 1/2 h composed epsilon, and then at the first order what I get is eta prime, where eta prime is simply eta epsilon prime evaluated at epsilon equals 0. Perp dotted with eta dot plus 1/2 mod eta dot squared. So now kinetic energy is coming into the game here, and then minus gradient h composed eta dotted with eta prime dA. Right, so obviously there are more terms, and I haven't really specified in any way what the eta prime is going to be. And now comes the key point. If one looks at, for example, the semi-geostrophic equations or other balance models, for example, the L1 model, which was first derived by Salmon, then what one finds is that essentially the way that the dynamics is reduced to the slow dynamics without gravity waves is that the continuity equation is left essentially untouched, and the momentum equation becomes a kinematic condition from which the velocity can be computed. And structurally, that happens whenever the Lagrangian that we obtain by whatever approximation is affine. And with affine I mean if the Lagrangian has the structure L equals let's say f of eta dotted with eta prime, so dotted with the velocities plus g of something that depends on eta only. So that is what I call an affine Lagrangian. And if you do basically the derivation of Euler-Lagrange equations, you'll see immediately that what you get is a kinematic relationship between, well, the h field and the velocity. And moreover, by the same Noether principle derivation, one gets an associated PV that is conserved under the flow, and of course one gets conservation of energy essentially for free. Alright, so how do I make my Lagrangian affine here? Well, what I have to do is I have to cancel this quadratic term, and I have free choice of the eta prime because that's the first order term in the expansion of the vector field that generates what I might see now as a transformation between the physical coordinate framework and the flow map in a new coordinate setting in which I wish to compute the reduced model. Right, so in that case, the Lagrangian degenerates, so let's call it degeneracy condition. And, well, that is that eta prime perp plus 1/2 eta dot should vanish, or more generally, I can have this some other function of eta as long as it doesn't introduce any time derivatives here. So that's the general condition, and maybe I can write this back in Eulerian, in terms of Eulerian vector fields. That's 1/2 velocity perp, and what we have looked at is a particular family of terms that can be chosen here, so one can make it arbitrarily complicated without much use, but we were looking for terms that are dimensionally consistent, and so what I add is arbitrary gradients of the H field, and obviously if the system was in geostrophic balance, so epsilon was equal to 0, then we would have a proportionality between these two terms, and so I'm essentially under the assumption of geostrophic balance varying on a line, pretty much.
What would happen if your arbitrary term was just 0? So what would you get from that?
I get a particular case, so that would correspond to lambda equals 0 here, and that is actually a good model that comes out. So one interesting choice is lambda is equal to 1/2 for the reason that well, geostrophic balance is U is grad perp H, let's say plus higher order terms, and so under the assumption of geostrophic balance, this vector field just is 0, and if we are not balanced, this vector field will be 0 up to the formal orders or second order accuracy of what the model is. And then one can compute the dynamics which are without actually transforming from one frame of reference to the other. Okay, so I'm not going to show you here how to get the equations of motion from there, but it's the usual variational principle. One just has to keep track of all the terms. And the result at first sight doesn't look pretty. So let me just write down what we get here. And
which choice of lambda would give you
QG is not in this framework. So I can actually analyze also QG in a similar framework, but it turns out what is happening with QG is that you essentially reduce to an advecting velocity field which is divergence free, and then you lose essentially the continuity equation as something non-trivial, and the momentum equation sort of remains, and you can take the curl and get some kind of vorticity equation. And then you can interpret the transformation as essentially restoring weak compressibility. All of this is formal, what I'm telling you here. So in QG there are some, if one wants to do any analysis beyond what is known by sort of taking the purely analytic approach, it doesn't seem we can add very much, so that's why I sort of crossed it out from the discussion here. But in principle one could see the transformation that one is getting in QG, something that restores weak compressibility, sort of a kinematic compressibility effect to what is essentially a set of incompressible equations of motion in the model frame.
How do you get SG in which choice?
So SG, that is another story. Maybe if I have 5 minutes in the end. No, SG is actually not part of these models, and it's not part of this hierarchy at any order actually, so one can show that. Very roughly speaking, and maybe I can make that more explicit in the end, you get SG by a selective expansion of terms in the Lagrangian. So some terms you keep unexpanded, so it's consistent to the same order as some of these models. And here the approach I've taken is essentially full expansion. You plug in, you do formal Taylor series, and you throw away any term that has epsilon squared or higher. Right, so this is the kinematic HU relationship minus mu to H Laplace H plus grad H mod squared, where sigma is lambda plus 1/2 times epsilon and mu is equal to lambda epsilon. So I'll comment on that in a moment. The second thing that we are getting is PV from either such a computation or guessing and direct verification, and that in this case looks like 1 for the Coriolis parameter, so in general this would be f plus mu Laplacian h divided this is sigma Laplacian h here, and that can of course be written, well, formally equivalent in the way that QH minus sigma, or let me write it as Q minus sigma Laplacian as an operator on H is equal to 1. Right, so at first sight this looks like a big mess, and it turns out that in the special case that lambda is equal to 1/2, so this prefactor is 1 here, this is nothing but the L1 model that Salmon wrote down in 85, and he found, well, he did a little bit of analysis, but then he found it too complicated to work with and proposed simplification, which actually turned out to make things worse. So L1 is a good model. And I want to give you some brief motivation of why these models are good, because there are sort of two magic things that happen, although this looks like a bunch of complicated terms with no visible apparent structure. There's actually a lot of structure in there. So the first thing, which I won't expand in detail here, is that, well, how are we proposing to solve these equations? PV, by construction, is material transported. So if you think about the analysis, that means the L infinity norm, or the minimum and maximum of Q, will be transported along and never change. So that should be sort of our base setting. And the second thing that is relatively clear, if you look at the important terms here, the highest order terms, is it's H-weighted or sigma H-weighted Helmholtz operator here on the left hand side with some junk terms. So we better have a positive surface height in order to not get into any degeneracies. So for solvability, it seems more or less necessary to start with a positive PV. One can talk about what happens in degenerate cases when PV goes to 0 at points. So, but in the worry-free case, one would like a strictly positive PV with a positive min, a positive non-zero min, and a positive maximum. And then by the maximum principle, one can show that the same from this, well, elliptic relationship between Q and H, the same holds true for H, namely H is bounded between the min of 1 over Q and the max of 1 over Q. So that's classical elliptic maximum principle. That means as long as Q is good, it will remain good for all times. That means H will remain good for all times. So that's the first nice structural feature. So this implies something similar for H. Right, so the next thing one needs to look at this more involved looking operator on the left hand side, and if one just wants to get a first result on solvability of this operator, one uses the Lax-Milgram theorem. So one has to basically associate with this operator a bilinear form and show that the bilinear form is coercive. And what turns out is, well, the obvious bilinear form with equal arguments, again, I shall not do the computation here, but what comes out is one gets 1/2 1 plus QH mod U squared plus sigma H mod gradient of U squared. Right? So basically under the conditions that are invariant in time, this is a nice coercive bilinear form, so continuity is obvious here, and coercivity, you see it from looking at the terms here. Right, so that gives coercivity. And the next thing, so this is now a two-dimensional fluid equation, sort of abstractly, this could be written as the obvious transport equation.
Is this first term in U of U supposed to be positive definite? The 1 plus QH term?
Yeah, so I have to be able to bound the H1 norm from below by this.
That's positive, right?
It needs to be positive, but basically if I have this condition on Q, I get that condition on H. So QH is going to be positive, so I'm not going to run into trouble here, and the same here. If H is positive, then I have a positive coefficient in front of the square term. Right, so everything is nice and good. So with some, let's say, inversion relationship, which is, for example, encoded here between the potential vorticity and U. So in the classical 2D Euler case, this would be just the Biot-Savart. And of course, there's a lot of old classical theory about 2D Euler, and the main observation for equations of these types is, suppose I want classical solution. Well, what do? I need to estimate arbitrary derivatives, let's say m derivatives. So let's compute 1/2 d by dt d alpha q squared in L2 for such an equation, and what I get is hitting this with this derivative operator, so I can probably estimate the time derivative by something absolute value. So I get an integral d alpha q u dot d alpha q dx, so this is all Eulerian here, and then plus a whole gradient here, plus a bunch of terms which are not any worse than the term that I've written down here. Okay, so you recognize the u dot grad here as being a perfect derivative on the alpha q, so I can essentially write this as 1/2 u dot grad d alpha q squared, integrate by parts, and then bound this term by u in w1 infinity, and then I get again the L2 norm of d alpha q squared in L2. And I get a bunch of other terms which are the same or better. Right. So if you would like to get globals,
So that last line, so what you pick out, that is the grade, so the gradient of u matters. Right?
I get the divergence of u, so I've been a little sloppy and I'm estimating all first derivatives here. So for this term I literally need the gradient of u. I'm getting other
I know to the Euler theory, the gradient of u is part of a critical estimate as well. So it's controlling the velocity gradients is the key thing in to the Euler argument.
absolutely.
So that's the same here.
That's what I'm hitting. At here.
How much more have you got? Because we've always got another talk. So
Right. So let me just finish this up, and then we can 2 minutes.
I hope you have 5 minutes. Let's say that'll be 5 minutes. Would be okay. But I mean, probably want a little break before Valerio's talk as well. 5 minutes is fine.
I think that should be fine. So in order to get, let's say I want global classical solution, and the argument for uniqueness is actually very closely related to such estimates. If I can show that u and w1 infinity is less or equal to, well, ideally we would like something like that, but we know this is not true because elliptic regularity doesn't extend to L infinity. I mean, not even in the Biot-Savart case this is true, but what is true there is that one can make it work with a logarithmic correction factor for, let's say, high enough derivatives. Let's say hm for m large enough, so larger than 2, for example, would work here. So if we have such an estimate where essentially this high derivative norm comes up with no more than a logarithmic factor, and we have a conserved quantity, then we get an estimate again that is valid globally on time, and that's essentially how all the classical 2D Euler, or most of the classical 2D Euler theory is developed. Right, so how do you prove such a thing? Well, if you have the Biot-Savart law with an explicit kernel, you can do the usual estimates on the kernel. If you look at this set of equations, it's the inversion from Q to U is not even linear, although I can sort of analyze it as linear problems, because the data, if you look at this problem, for example, the data is sitting in the coefficients. It's not on the right-hand side here. So as a map from Q to U, everything is nonlinear here. So I've no chance of working with basically estimating convolution kernels. And now a trick comes that is essentially due to Udovich in his 63 work on 2D Euler. Namely, Udovich noticed that you can get estimates like this, and he mainly used it for uniqueness in that paper. You can get estimates of that type if you essentially show that U in W1, P is less or equal to CP Q LP for 2 less than P less than infinity. So essentially, if you can show that you have a controlled explosion of the constant in the LP elliptic estimate, and I'm not sure if he was the first one, but he certainly wrote a paper on proving that for second order elliptic operators, that an estimate like this holds true, and it's now part of the classical elliptical LP theory. And now such a thing this estimate implies this one, so we are good for classical solutions, and this is actually something that can be shown in this more complicated framework as well. And if you realize how to do that, then it turns out that except for subtleties that relate to existence of weak solutions, the spaces are too weak, so the nonlinearities show their nasty face. But for classical solutions and for a large part weak solutions, we are really in the framework of studying 2D Euler in the vorticity form. And that holds for a range of values for lambda. So in particular, it includes the Salmon L1 model. It includes the case where lambda is equal to 0 and various terms drop out here, and one gets sort of nicer expressions, but has an explicit transformation. And the estimates leading to that essentially recast all of these relationships in terms of fixed point principle, which are numerically tractable. So you have basically numerical prescription as well on how to solve this problem, and the numerics works as nicely as the analysis. And let me stop with that, and maybe we can take discussions of it.
We've parked some of our questions already. Are there any further questions now?
If I may, and looking back at QG, if you look at your model, so that's on the top or the bottom one, and on the lower part, the QG, the PV equation. If you take lambda as half, then the QG limit is in that model. So QG should somehow be embedded for the case lambda is half only, because you just see the QG. If you look at the PV advection and you do an expansion of H, right, you introduce a basic state, then you get QG. If you take U as per H, then you essentially have the affecting velocity, and that's it. So in principle, it should be embedded in there as a limit. At least from the equation, you see it immediately. So
I think you're right. So this is actually something we have on the plate with David, essentially pushing this into the QG limit and see whether it actually includes the QG limit.
It does. I mean, U is perfect.
But the QG limit also has the approximation for continuity equations. So will you get that as well?
Yeah, you do, because you just look at this in the end as a QG advection. PV advection equation, which includes all the QG terms. The prescription of the velocity field includes geostrophic balance, hence it includes QG, period. I mean, you just spot it. I can't see it from the variation in principle. It's only for the case lambda is half. I say that. It's in there.
Yeah, but what you cannot guarantee is that the advecting velocity field is divergence free. So it's clearly not identical to QG.
No, but if you take the limit, if
Right.
you,
Yeah.
cut sigma in that top equation and mu, you get the geostrophic velocity, which is what you have in QG. That's the affecting field in the PV. The PV can be simplified, includes all the terms of QG plus more. Hence, QG is embedded. Period. For lambda half only. So it's in there.
I'll let you look at that more. Any other questions? One very little one. So it's, what you said just more or less at the end, you sort of implied that there were few sort of reservations you made in what you said about normally things getting nasty for weak solutions and so on. So is there actually rigorous, not long time existence proof for this?
Yes, we have a proof long time existence of weak solutions, and essentially where things get nasty is if you you approximate this system by a sequence of approximate solutions that you can do in various ways. For example, you can take classical solutions that at least that's the way we do it, and then you have to pass to the limit, and what you need is you need to show that this operator here is uniformly continuous. And now for a linear operator, if you just have a mapping in certain spaces, the uniform continuity comes for free. Uniform basically in PV fields that are bounded above and below in the proper way. But here now the problem is nonlinear. That means one has to show uniform continuity of this operator by explicit estimation, and these estimates are more hairy than simply looking at mapping into balls in certain spaces. And what we have is that we have a strange restriction on the lower limit, but this seems to be relatively fundamental when working in this analytical framework, that the Q min needs to be, I forgot exactly what it was, there's a root 5 coming in. There's a numerical constant that you need to require the Q min to exceed.
If you impose that, it's obviously very robust, but then you have a rigorous result.
That's right.
I think we'll probably better stop now. Thank you very much indeed.